Good morning, welcome to Control Systems Seminar and Webinar. The last sessions we saw about the transfer functions, resolving the transfer functions using partial fractions and then applying inverse Laplace transform to such functions to arrive at some analysis about the control systems. We used polynomials for that, and now we are going to see some of the system which is going to be consisting of blocks and units, such that the system transfer functions are going to be analyzed. First of all, we need to know what is transfer function. Transfer function is a representation of a system output in terms of its input, either as a ratio or as a function or as a domain transformation function. This is called as a transfer function. Transfer function is for easy numerical computation. We have different transfer functions depending upon the control system blocks. There are different control system blocks. First of all, we need to see the different control system blocks. We have the blocks in cascade. We have the blocks in cascade. We have the blocks in feedback path. We have the blocks in manipulation. Then we have the takeoff point. We have the blocks in series. We have the blocks in parallel. We are going to have the blocks in parallel leading to a summer or a subtractor, etc. So these are the block units which are going to construct a control system as a whole. Depending on these block systems, we have many definitions on the transfer function. We have a direct transfer function which is called as a forward transfer function, which is represented by a letter, alphabetic letter. Similarly, many transfer functions are represented by alphabetic letter accordingly. We have the forward transfer function, then we have the feedback transfer function, we have the loop transfer function, then we have the closed loop transfer function, we have the active error ratio, and then we have the primary feedback ratio. So we have all these particular transfer function and ratios. You can see that these are represented in the ratio as we move towards the last, that is the error ratio or the primary feedback ratio. All transfer functions are ratios in short form, but the ratios are not just values, they are ratios of functions. That is the uniqueness of transfer function analysis. Now we have seen many transfer function. One is the direct transfer function, forward transfer function, feedback transfer function, then loop transfer function, closed loop transfer function, actuating ratio, and then primary feedback ratio. All these things are denoted by separate alphabet terms. Um, to just describe a particular system depending on these particular ratios, it is very good to see that these ratios and transfer functions are dependent on each other. The purpose of classifying all these ratios and transfer function is to identify the dependency of each of these, such that the computations becomes easier in the control system computation analysis. Now we will see some of the easiest manipulation regarding the control systems in terms of the error ratio, in terms of the forward loop transfer ratio, and also what are the control system blocks which are going to be impacted and what this denotes in a nutshell, so that we will have the blocks arranged, and then the blocks will give us a knowledge about the units of the control system. And what you are seeing, C by R is going to be the control ratio or closed loop transfer ratio, which is given by G by 1 plus 1 by 1 plus G by 1 plus GH. This GH is called as a loop transfer function. That means it is a product of a transfer function, forward transfer function, and the feedback transfer function. Feedback transfer function is denoted by H, forward transfer function is denoted by G. So the C by R closed loop transfer function on the control ratio is given by this formula, and we have also seen another ratio now, E by R. E by R is a error ratio. E denotes error. Now this E by R error ratio says that it is 1 by 1 plus or minus GH. What it means is this particular forward control ratio has got the error ratio in the denominator multiplied by the gain of the system. So gain of the system is going to be against the error ratio, such that the control system is going to be adjusted between the gain of the system and the error ratio. This is called as a automatic control system. Then we have the B by R. B by R says that it is a loop transfer function. Loop transfer function divided by the 1 plus GH. 1 plus GH is nothing but the error ratio. E by R is 1 by 1 plus GH. So loop transfer function multiplied by the error ratio is going to be given as the primary feedback ratio. This is called as a feedback ratio. So we have the feedback ratio, that is the multiplication of the loop transfer function along with the error ratio. Then we have the error ratio. Then we have the control ratio or the closed loop transfer function. In short, we can say that closed loop transfer function is what we want in a particular control system rather than all these particular ratios. It is good to have this formula to easily compute the control system behavior depending upon these particular ratios. Now we have the control system blocks. Control system block has got the forward control ratio, as you saw. We only saw the ratio, but we didn't see the blocks. Now we are going to see the blocks and what they are going to indicate, so that it will give good understanding about the correlation between the blocks and the ratio. We have some as our manipulators as the signals entering into the particular control system. It may be a summer or a subtractor or anything. Just we can see this is a typical example of a control system. It contains the blocks, the product of G and H, which is called as a loop transfer function. It is going to decide what the entire control system is going to do. Now we have the error signal E, and then we have the feedback ratio signal, which is going to be a contribution from the H. You can see that the signal from the output is going to enter into H, the feedback path, and then the H is going to give the output B. The B is going to be either summed up or it is going to be subtracted with the incoming signal, and it is going to yield error or zero error. So this is going to enter into the forward G, that is the transfer function of the system, the direct transfer function or the forward transfer function of the system, and then it is going to yield the output. So this is a simple control system block enumerating or representing all these particular ratios. Now we will see some of the transformations. The transformations are very important. When we say transformation, it is not the Laplace transformation. We saw the Laplace transformation earlier for the polynomials, but now all are represented as Laplace transform blocks. The units in the particular system are represented as transfer function blocks, and these particular blocks have got many equivalents. The equivalents have to be represented in some form. That means if we see a block, that particular block equivalent is represented by a product of an equation. So this is going to be manipulated in a control system such that the analysis becomes much easier instead of solving block by block. Now we are in the unit level. We are not in the polynomial level. We are in the unit level of the control system. The units comprises of a lot of small systems or blocks, we can call. This put together, these units put together form an entire control system. So we can say that the units or the blocks are subsystems of the entire control system. There may be a feed forward system, there may be a feedback system, or anything as we design the control system. So we can see now can see one example now about the control system. We can see that there is a incoming signal x here, then we have a p1 p2, we have two gain blocks, then we have the addition summer here, then we arrive at the output signal. How we are going to manipulate the signal if we want to process it individually? First we have the x entering the p, then we can have px, then we have the x entering the same path, you can see the arrow here, then we have the p2x. So when they culminate in the summer is going to give either the addition or subtraction of these particular signals. And so I can say that it is a combination of both the signals, y equal to p1 x plus or minus p2x. So if I want to represent the equivalent of this particular control system, then how can I represent this particular system? I have the incoming signal x, then I have the block as p1 plus or minus p2, which is going to give y. This is the representation of the control system from the unit system level to the block system level. So this is a unit system level, this is a block system level. You can see this is called as a block transformation of control system. Similarly, we can have many other control system. This is one feed forward, but we will see the feedback. I have the summer before. So what will happen here, interestingly, I will have a block here and I will have the P2 here. My aim is to manipulate the signal depending upon the control system functionality and the arrow diagram. Here you can see the y output, it yields a y, then I sample the output. Now you can see here, this is an interesting one. I give the x which is going to be given to the summer. This is summer. Now how can I see this particular y? I can say that y, this is the y signal, y, the y is going to be equal to p1x. What is p1x? Here you can say that the x is going to enter here, then it is going to enter the p1, so it is going to come here p1x. Then the x has already got the p2 path, the p2y is going to come here, it is going to add up with or subtract with the x. That means the p2y I have, that is going to come up here. So p2y, y comes here, p2, it becomes p2y here, it is going to add up with the incoming signal, but it is going to travel into again p1, so it is going to be p1. So you can have p1x as 1 first, and then second unit is you can have p1 p2y. So what it gives me as a whole, this particular product is going to be evaluated in terms of y, not as x and combination of y. We have to rearrange this particular equation such that we get the x as input signal, and then we get x minus 1, then y. So what we have indicated here, it is a rearrangement of these particular signals and units, and we have the x entering into this particular system. We have the p1 by 1 plus or minus p1 p2, then it gives the output signal y. By rearranging this particular equation, I am getting this form. So this is called as a canonical form representation or transformation of this particular control system. The control system blocks may be huge, but we need to represent in a very good diagram in a canonical form such that we arrive at the output of the signal function. This is what we are going in control system. So representing this is a big task in a control system, so that the control system has got lot many advantages by representing these canonical forms and the transformation theorems. The control system canonical form and transformation theorems has got reduction of complicated block diagrams. When we use the transformation, the cascade blocks can be combined in one form and the parallel blocks can be combined in one form. The series blocks can be combined in one form and the minor feedback loops can be reduced. So this is a reduction of complicated block diagrams such that we want to avoid the complicated block diagrams and then represent these particular block diagrams in canonical form. Canonical form directly gives the transfer function of the system in a simple term. So this is one type of algebra which is involved in reducing the control system transfer functions, and then representing the blocks of the control system transfer function in the easiest manner, such that it can be reviewed at any point of time. When we do the canonical feedback control system transformations, we have to keep it in mind the signs of the particular signals entering the feedback paths and leaving the feedback paths. This is very important when we have a block of summer or a subtractor in the middle. So this particular summer and subtractor is indicated by a circle by giving a sign to this particular circle. It may be either positive or negative, but if both positive or negative signs are indicated on the circle, then we have to do both the possibilities. It may be plus or minus. Hence you can see the equations in the denominator representing plus or minus. That indicates that it may either be a summer or a subtractor depending upon the configuration it is tuned into. So this is called as a canonical representation form. Then we have the feedback systems unity yielding to unity feedback systems. That means the signal is going to be just given